Yeah. Okay.
Okay, so let's start the talk by Dr. Fan. Before starting his seminar, I will introduce you. I will introduce Dr. Fan. He was one of my colleagues when he was a postdoc at Tokyo Tech, and after that he moved to Riken BSI, Toyo Izumi Group, and he is now an associate professor at San Yatsen University, Chuzan Daigaku in Japanese. Today, he gave a talk about recent progress in deep learning from the viewpoint of statistical physics. I think his research will provide a fruitful connection between statistical physics and deep learning. So, and we will have a short question and comment session in the middle of talk. And of course, you can you can ask question anytime you want.
Yeah. Okay.
Please start.
Okay. Now let's. So now I can start, right? Yeah. Okay. Could you hear me clearly?
Yes.
Okay. Now I play the full screen. But if you have a question, then can you ask at any time? And I want to I like to explain in the when I discuss on that point. Yes, now it's my honor to give a talk at the Institute of the Statistical Mathematics. And now today my talk title is Data-Driven Effective Model of the Deep Learning. Okay, now I give the background. And as we all know, in deep learning, there's a generalization paradox because in modern practice, very rich model such as neural network are trained to exactly fix the data. But classically, such model would be considered overfitting. This is from the statistical learning theory. But in practice, they often obtain high accuracy on test data. As we can see now, many outstanding performance in the academic field or in the industry field. But this is, of course, is apparent contradictions. And has already triggered a lot of researchers come from different disciplines to understanding what's the origin of the generalizations. Because even in the biological system, people can easily to put an equal between the generalization to intelligence. Because if you can generalize from your data, we know the machine or the algorithm can get the physical law or get the rules underlying the data. Then we call this maybe an intelligent agent. But nowadays, in the deep learning, we could not understand what's the origin of the generalizations and how to propose a framework to understanding these very fundamental important questions now becoming a very hot topics in the fields. So I propose to review some current viewpoint, and one framework is called NTK. NTK is a neural tangent connect. It is argued that the deep learning maybe is a connect learning, and for example, if you look at the bottom figure, they call. The NTK always focus on assume the neural network has a very wide width, right? And then if you increase the width of each level, and then the searching for a solution is things narrow down to the initial parameter, because we know initial parameter is commonly random, right? It is very easy. You have even have analytical solutions. But if you put the width to infinite limits, and then the solution can be get very close to initial parameter, and then the connect it can be very it can be data independence, and then the analytical analysis is very easy or checkable in this limit. So we can summarize NTK as infinite width, right? And also low learning rate. This low, it is very small learning rate of deep learning, but with random data independent connects, and then you can put into the understanding of the many phenomena. This is on the asymptotic limits of the neural network architectures. On the other hand, we have found the double descent, right? On the top, the figure, and you will find the P is trainable parameters, right? And the M is a number of the data. But the parameter, the number of parameters is more than the data, and then this is under parameterization, and then the losses is will decrease until the P equal to M, and then the loss will be at a peak, right? And after that, that is now our current modern neural net will always use our parameterized, and then we will see the lower test errors in contradiction with the statistical learning theories. Of course, the NTK limit is according to the parameter, number of parameters much larger and much larger than the number of the trainable, the number of the data point, and this NTK limits. But of course, this paper, there also a very recent paper argue that there's not the double descent, maybe a triple descent, and there's a lot of theory to interpret this phenomenon, intriguing phenomenon. And on the other side, on the mean field side, and also people use the classical, and this mean field is the statistical physics because the width of each layer, it is larger enough, and then you can use the local field of each neuron can be considered as a mean field, and you neglect the fluctuations. And this is a very classical viewpoint from the statistical physics, maybe in 1980s, and this mean field viewpoint. And so now we have at least at the two main points, that is NTK and mean field. But NTK is much more restricted viewpoint because they need the infinite width and the low learning rate. Okay, now another perspective, it calls the geometric perspective. This is a recent the observations that is in 2018, right? In these two paper, and we already know the training neural network is equal to minimizing of complex and high dimensional and non-convex loss, right? But the interesting things the engineering found there's if you look at the two local minimum or two local solution, and you can optimize a path, and this path can connect these two minimals, and along this path, and the algorithm could not encounter some high loss barrier, and you can see in the right plots, and there's origin curve, and there's compared to the blue one, and then you will see origin curve has no encounter the high the barrier of high loss. So this means that from the geometric perspective and the energy landscape or the solution landscape of the deep learning system may be not as complex as we previously expected. So then this is as a motivation for our work, and this is empirical observation is just to detect the local the structures of the energy landscapes or the solution landscapes. So And this is another paper in the PNAS this year. They say that compared with the grassy dynamics in the spin grass and the agrarian or the local dynamics also suffer from the trapping local minimal. But the recent numerical studies show that the absence of high barrier between minimal around techniques such as the vertical gradient descent to reach low-lying solutions in the log surface. So, and this motivate us to propose a global viewpoint of the geometry landscape in the deep learning waste solution space. So the question now is, do we have some effective theory of the practical deep learning? So this is two features we want to focus on. One is non-NTK, because we know NTK near infinite width and very slow learning rates and data independent connects, right? This is maybe it is not realistic phases of the practical deep learning. And the other point, we do not try to focus on local view, and we want to focus on global view. A local view means that you just find a path connected to two solutions, and you can draw the disconnected graph or clustering the solutions you get from the SGD dynamics. But we want to propose a global view. Global view, it means that you should capture the how these connections in the deep network interact with each other, and then you try to propose an effective model. It means that in physics, it just you write down a Hamiltonian, and then the Hamiltonian capture the interaction among the wave components of the deep network, and then you just to analyze those Hamiltonian, and then you get the global pictures about the deep learning, and that is our motivation to focus on this is two distinct viewpoints. So our setup is very simple, and first we want to put a small scale neural network first to study a small scale neural network first, because of course we could not. At the beginning, we could not start study the VGG or those huge model that Google use. But we just to try to search some principles from the small scale network. Then we should do the PCA on the real data, right? You just get the low dimensional projection, right? For example, from the for MNIX, we forced to get the 20 dimensions, but 20 dimensions is still larger for the neural networks, right? If you want to do the classification, it's still a non-trivial task, right? So we forced to do the PCA for the 20-dimension projection, and then this is the first layer of our neural network we consider. And then we built up the hidden layer. The first hidden layer just has 15 neurons, and then the second hidden layer 15 neurons, and then we read out with the 10 neuron corresponding to the 10 classes of the MNIX data. So at this architecture, we call the first layer to first hidden layer, the input layer to first hidden layer as the lower bound, left boundary, and then the connection between the first hidden layer and second hidden layer we call the interior. That is the central part of our deep neural networks, right? And then the connection between the last hidden layer and the output layer we call the right boundary, right? So this LB, ITI, and RB is our shorthand for the following analysis. ITI is just internal, and then the left boundary and right boundary, right? So this is very easy to be image about the deep learning network. Of course, if you for the very deep neural network, and then you have more internal layers, right? Here we just focus just only one internal layer. Then when we finish this architecture setup and our data after pre-processing, and then we can train our neural network. But here, when we're doing the training, we assume the connection is binary because we want to map this deep learning model to a physics model that is as a spin, right? We know the spin can spin up and spin down, and this is very common language in the statistical mechanics. We want to do this mapping. So then we do sampling, right? After training, you can sampling because you're starting from different initialization, and then you will probably reach on different target point, right? And then you can sample many configurations of the solutions, and each configuration can realize the same test error or similar test error at the same level. For example, above 80% of the accuracy or something. And then after you get these samples, and then you can analyze the weight statistics, right? From the minimum model perspective, you can estimate the first order moments. That is we call the metization in physics, and also the second order moments, and then we call correlation or 2-point correlations in physics. And we assume at this level, our model can describe the original deep learning very well, and this is our assumption. We can test this assumption later. And then from these things, it's very common. This principle we call the maximum entropy principle, and it really has a very long history in the physics and even in the statistics. And in physics, we call that, we construct an Ising model because we focus on pairwise correlation between the weights. And then we construct Ising model. And then after we get the Ising model, we get the effective model of the complex deep learning networks. Then if we have the Ising model, and then in physics, we can analyze their landscape structures, right? This landscape is not local. It can be studied in the global view because this landscape is supported by all the interacting ways in your deep learning models, right? This is our basic framework of our setup. In the following, we will explain in detail. This is 3 steps of our model setups. So now we first to introduce our training, how to do the training. The training, we assume the way is follow a probability distribution, and this is a binary has 2 peaks, right? One peak as a 1, and the other peaks as a -1. This is for example, in biology, you can call the 1 is the excitatory connection and -1 is inhibitory connection. And each peak has a certain probability, and this probability is a Simoe function, and then they're captured by our theta, and theta is a field, right? In physics, it's an external field to control how biased or for this way, taking 1 or -1. With this kind of probability, and then you can write is average of the way, right? Or there's a second moment of the way. Because these 2 statistical parameters is very important for training, for the mean field training, or we can say. So this is perspective is a mean field perspective, right? You assume each neuron in the hidden layer receive a large number of the inputs, and then you can assume it follows of the IID of the Gaussian distribution, and then you can analyze his pre-activation can be as a Gaussian random number. Pre-activation is G, right? The last equation, the G I show here, and then it is equal to the mean plus the variance times the independent Gaussian random variables. You can check that this is G is follow a Gaussian distributions. This is a reparameterization trick. this tree also used in the variation autoencoder VAE, right? And then the activation, it is passed from the leaky ReLU, right? ReLU, the nonlinear function. And then the training, now the training of this neural network is transformed to training the local field, the external field, the theta ij. This local field, after you get this local field, and then you can get the distribution of the way, right? If you get the distribution of the way, you can do sampling as many configuration as you want. This is exactly fit our purpose of our effective models. So this is the basics of the training of our deep learning systems. So now we go to see the primary result, right? So the first, the left fig is so the training error, right? We use a cross entropy, and then the training error decrease as you approach goes, and the test accuracy also increase. For our model sector, we can train the system up to the maybe 85% accuracies. And this is makes sense because, of course, if you can use a large scale neural network, you can reach 98 or 99% accuracy. But here, first, we use the pre-processing of the PCA, and the other, our neural network architecture is small scale, and I think this accuracy is optimal, almost optimal. So the left figure we shows that our training method doesn't work for our purpose. The right hand side is shows we're doing some TSNE, the visualization about the solutions we get from our training. The green one is initial solutions because you initialize the theta, the local field. You can have the initial weight distribution, right? The two peak, the Bernoulli distribution, and then you can sample the initial states. This is shown by green. Then from this initial state, you can train your system maybe up to 200 apples, and then you arrive at some targets, at some solutions. And these solutions we call the blue one, and then you can see the green one is much more dispersed than the blue one. So it means that the final training state it has been reached by a very small regions in the huge weight space. From this visualization, of course, it is put on the low dimension. That is two components. We can already see maybe there are some structures inside the solutions we reach by our mean field training systems. So this is we get the initial results about our systems. So this is the TSNE visualizations. Now we can ask the next questions is, can we get the global view via the physics models? So this is our next steps, the purpose. So to get the global view in physics, you should build the effective model first. So the effective model, as I say, we choose the maximal entropy model because in statistics, it also a least structure model because you give only the pairwise correlations. You want to build a network of interacting elements. So now we write this is a distribution as a Boltzmann distribution, right? And the sigma now is the way, right? It's the connections in our deep networks, and the energy or function or the Hamiltonian, and it can express as it can be captured by the Jij and the Hi. Jij is characterized the interaction between two waves, any two waves in the deep network, right? And Hi is a bias because during the training, our polynomial distribution for the waves can be highly biased, right? This is captured by the local field for each wave, HI. So the Jij and HI is an interaction in our model. It's completely different from the interaction in the deep network. So this is two different concepts. So now we have a lot of configuration of the connection of the deep learning parameter, right? So how do we know the Jij and HI? And this is easy, right? If you follow the maximum entropy principle, you can write it as a gradient descent on the maximum likelihood, right? And you can derive this is a gradient descent its equations. If you try to update the Jij, and now you should get the two terms. One term is correlation come from the data, right? It is fitting the correlation in the data. And now the second term is correlation in your model, right? Correlation in your model, we already have many methods to compute. For example, mean field measure and belief propagation measure, and also you can use directly the deep sampling, right? And this is easy to be calculated. And of course, this similar holds for the field, right? The field, it is just the first order motion for each wave in the data, and the first order motion of each wave in your model. And the model, this model is referred to the Ising model, or the above the Boltzmann distributions. So this is a classical procedure to get the coupling, the coupling interaction directly from the data. I think this is a model setup. It is very popular. I think a few years ago in the neural networks, they also call the inverse Ising model. That is, you know the data and try to construct the model parameters from the data directly. And this is what we call the statistical weighted approach to infer effective model of the deep neural networks. So this is our model setups. So now the third steps is landscape analysis. After you get the model, how to analyze the global view of the model, of your model. And then we just write up our free energy, and this free energy we add up a second term, and this term is has a external field, right? This is term we call is a random field term, and it's sum over all I. I is now you can interpret as waves in your deep networks, and sigma I star. The star is a reference, point, because you want to detect the landscape in your deep learning space, and then you should choose one point, which point is should be a reference, right? Because if you think about the picture, that if the landscape is very large, and then if you put on the different reference, of course the landscape may be very different. But if the landscape is convex, it's very smooth, then I think if you choose a different reference point, I think the landscape may not difference. So this is our purpose. Now we set up our reference, and this reference, how to choose? You can choose the low energy, the configuration, or the high test accuracy configuration, because you can choose those good solutions in your deep learning landscape, and then you try to see how is the geometry pictures around that good solutions. So this is our motivation. If you add this term and this term, the effect of this term is controlled by the coupling field. We call the X the coupling field. Before the last sum, this is X is our coupling field. So you can tune this coupling field and to see the structures of the landscape. It's very intuitive. If the X equal to 0, of course, this is totally random, right? It doesn't suffer from the constraint from the reference. But S is very big, or maybe go to infinite. And then I think the landscape should be constrained to very near to your reference. So you can tune the X to see the landscape viewpoint from different separation from your reference. You can tune the landscape. Later, I will show our simulation results. So after define this is free energy, and then you can write up into integral, transform to the sum over configuration into the integral of the energy density and the Q. Q is overlap. Q is just it characterizes how far the reference from the equilibrium solution of the model sigma. So now you transfer to the integral, and then you can use the set point method to analyze to get the expression for the free energy, right? So you can get the three concepts. That is energy, entropy, and geometry. And geometry is characterized by the entropy function. And this entropy function, the definition is follow the Boltzmann formulas. Because you're forced to count how many solutions at a fixed energy level, right? And the other point is count how fast from the equilibrium solutions from your reference. This is characterized by Q, right? So we have two arguments. One is epsilon, the other is Q. Epsilon is the energy level of your equilibrium solution, and Q is the distance from the reference. And I think this is two arguments can characterize interaction between energy, entropy, and geometries. And this is what we so call is our landscape analysis, or the principle underlying our landscape analysis. So now we see some basic result for the deep learning. And the first picture, it is we can train the IC model. We can learn the IC model, use the data come from the different parts of the network, right? You know, in our deep learning network, we have three parts: the left boundary, internal, and the right boundary. If you model the deep learning as an entire framework, the full neural network, and then you get the coupling and the bias distribution, just like the leftmost, right? The figure A. Then you can see the coupling is constrained to around 0, right? The coupling is not very huge. And the bias, it seems, has broad distributions from the negative value and to the positive values. So it means that the solution you get from deep learning, it can be has a certain probability to be biased to the always to be +1, or sometimes it will be biased to always to the -1, right? So this has a heterogeneous structures. And you look at the figure B, and this is the full network. Still at the full network, we can see the correlation come from our model. It almost fixed correlation come from the data. That it means that our training can reproduce the second order correlation observed in the data. And this is the first requirement for your model to become effective, right? So in the figure C, we can see still a full network. We can see the energy energy of our IC model. It seems to has a correlation with the test accuracy from the deep learning networks, right? Because we sum the deep learning solution and then construct the IC model, and we found the IC model, if the energy of the IC model is low, and then the accuracy is probably high in your deep learning model. So this correlation sounds our model can be effective. It has a one-to-one correlations between the energy and your test accuracy. So the energy landscape may be, in some sense, they can reflect the test accuracy landscapes. So the last week is history about the 3 parts, right? We can also study the different parts of the deep network. For example, the blue is the left boundary, and the green is the right boundary, and the yellow is interior. So the bias of the interior, you can see the history is very distinct from the left boundary and the right boundary. Right? Even for a coupling, they also has a sharp peak around the small range of the around between GLO within the GLO. So from this figure, we can expect that maybe the internal part has very distinct properties in the compared to their 2 boundaries in the deep learning networks. So this is the property of our IC model we learn from our data. Now we try to see how effective of the IC model, right? The one criteria you try to see whether the model can predict the high order correlation, right? Because in the deep learning network, they may inject the high order correlation among its weights. This is intuitive. Now, if we set the deviation criteria, right, then we see a bug of our prediction. For example, you see the figure B. If the deviation criterion is set to lower than the 0.03, and then you can get about 90% of the prediction. It means that the construct the effective model, it can predict some intrinsic property in your deep learning original models. But of course, we could not say this is a completely perfect model, right? It still had some higher order correlations. It cannot be predicted by our current model, but our current model can predict a large percentages, we can say. So now we study the first region under parameterization, and this region characterized by the number of parameters divided by the number of the data. In our case, of course, the number of parameters it is 675. Our data it is full data set 60,000. So this is alpha. It is around 0.01. We can call this under parameterization. And in our network, we get a very surprising result. It means the internal label. The internal label is a depth dot line. It almost saturates the upper bound. You know, the upper bound is means that you assume that every connection, every weight is a random one. That is a completely random one, and it will give you upper bound. But in the deep learning network, we found the internal parts, it almost saturates upper bound. That means that the internal part has most number of the degree of freedoms, right? So this is so the distinct property of the internal parts. And then you call you see the left boundary and right boundary, and then you will find the left boundary is smaller than the right boundary. The entropy curve, right? So it means that the left boundary is much more constrained than the right boundary, right? So another feature is that in this landscape, we do not find any discontinuous transition. That is like the insects, because insect it is a distance d, right? The distance d is from a distance from your reference, right? And then you change it with the coupling field, the x, right? The x in physics, if there's some first order transition, for example, you tune x, there's some metastability or memory effects, and then it will signal the logic structures in your landscapes, right? For example, there's a very high berries, and then you can see the discontinuous transition. But in contrast, in this underparameterization, we never see any first order distribution. That means that the landscape is smooth, right? It has a very big components, and then all of the solutions can be connected locally within this is big components, and then our landscape curve captures the global viewpoint about the reference solutions. So this curve is a mean of typical value of the 20 reference point. So it things doesn't depend on a reference point, and all the landscape it looks like not the heterogeneous. It is so homogeneous. It seems it has a smooth landscape. So this is what the first result we get for the underparameterization region. Now we go to overparameterization. The alpha now it is a parameter is still 765, and then our data we decrease our data to 500, and then you got this ratio is 1.3, about 1.35. But of course, we remark that this is not the heavy parameterized. It's not the true overparameterization region in the current deep learning. I think in current deep learning, maybe this ratio can go to the 10 or 100. It can because in our current academic or industrial application, the data is always limited, but the parameter can be go to a very huge the number of parameters, because the neural network can be maybe 100 layer, and each layer can be thousands of the neurons. So we emphasize this result is not for the heavy overparameter, it's just slightly overparameterized. But in this region, we also found a smooth landscape. Now the first order transition for the distance and coupling field profiles. And also we find the interior part is still enjoying a huge degrees of freedoms. Just like you can use any random ways, and it properly can be served as a true solutions. And this is quite surprising for the internal part. But for the left boundary and right boundary is still lower than the internal part. It means that it becomes much more constrained from the internal part. So now maybe we can reach a conclusion is for alpha proportion to 0 or alpha proportion to 1. And then maybe from the geometry viewpoint, maybe we can have same university class for the underparameterized and slightly overparameterized region. Maybe they enjoy the same smooth landscapes, and boundaries much more constrained from the internal part. This is what we get from this is effective model of the knowledge from our current neural networks. So for the shallow neural networks, and then we found very different properties. Shallow neural network means we remove all the hidden layers, and then the shallow neural network now we found the sectors, the sector space. Now you can see clearly there's a first order transitions from the insects. When you tune the coupling field, and then the distance can stay at up to some point, and then they jump up to the very far away. So this means that the landscape maybe has a very large and heterogeneous and localized chapters in the deep learning wave space. So this landscape you can see now it becomes a reference dependence, right? If you select the high energy reference or low energy reference or medium energy reference, the landscape totally difference. And also you can see hysteresis from the profile, from the distant profile. So it means that from this viewpoint, we can conclude that the depth may have the chaining, because the depth can significantly change the landscape viewpoint, the view that is the landscape smooth, that is has a very big chapters from the solutions in the deep learning space. So this is the shadow network. We found there's a distinct class from our previous under-parameter mineralization and over-parameterizations. So now we just put the internal part of the property internal part out, and then we make the model highlights the remarks about this internal region. It seems more freedoms, and it's just like behavior as a liquid. Maybe we can see a liquid in the physics, because the liquid already enjoying the more freedom than the solids or even the glass, right? So it implies maybe has a fast dynamics in the chaining. This has not been tested in the large scale modern deep learning chaining. So this picture, it is we recently found that from the other settings, we compute the model entropy. This model entropy is entropy of the wave connections in the practical deep learning systems. We also detect a peak for this entropy at the internal level, for example, 2 to 3 and 3 to 4. The boundary level is also much more constrained, and the internal level has enjoyed a large entropy, maybe a large degree of freedoms. This is consistent with our another theories. And also we mentioned the Yoshino Sensei's paper in 2020. They also found a liquid central path in his Toya model. I would say it is not the practical deep learning model. And in his model, they designed N L perceptrons. The L, it is a number of layers, and it is a wave in each layer. So they decompose of deep learning or deep network as NL perceptrons, and then in his model they calculate the partition function or the volume, and then this volume they chase up all the perceptrons the way and all the internal representations, the S, right? And this is to chase, I think, is very different from the practical deep chaining, because in practical deep chaining and the internal representation is dependent on the connections and your inputs, right? It is not completely independent with each others. But anyway, from this is a Toya model, they find a liquid central path, and this liquid central path they can be characterized by physics that is used autoparameter. For example, the EA autoparameter in the spin glass they found equal to 0. It means that they have a large degree of freedoms for the dynamics, and for the boundary near to the input or output, they find the solids that is much more constrained dynamics or the equilibrium solutions. But in our case, we never find this is solid state. Maybe although the left boundary and right boundary is much more constrained, but it's still below to the smooth landscape. It is not has a clustering or internal clustering of their solutions. So this may be because our model maybe is not the huge model or large model. Maybe this is a hypothesis. Maybe can be checked in the future studies. So now I go to some discussion point and to inspire from our studies. So this the first point is a global geometry view, right? This is a university class. Maybe we can clarify some university class from the geometry view for deep learning to solve some paradox and some intriguing properties of the deep learning. And this is the first point. And the second point, maybe we are bridge towards learning dynamics. Because learning dynamics, we already know now in the large scale deep learning model, learning dynamics do not suffer from high loss barrier, right? And even two solutions can be connected by a path with equal low loss. So this means that their intrinsic properties may be connected to the learning dynamics. We hope our method can offer an insights to this bridge. And the third point is the different parts of the deep neural network are not statistically identical. Maybe this point it is not recognized in the previous study because all people always treat the deep neural network as a whole, right? To analyze his statistical property. But in our study, we identify these three parts, that is boundary and internal, may be significantly different from each other's. And also they are related to the changing dynamics of the neural networks. So this is the third part, and the first point is the limitation of our study. But now, due to the changing costs and the sampling costs, our study now is still limited to small scale neural networks. Although this neural network is training use the current techniques of the machine learning, but this scale is still not compared with the modern deep learning model. But we will hope the principle we get from this small scale study can be generalized to the deep learning, to a practical deep learning or the realistic settings. So the last point is we hope this study can inspire the researcher in the field to think about a final effective model of the deep learning. Especially we can use the physics tool to study his free energy, his phase transition, and his a lot of the global structures of the models. So yes, now I finished my talk, and maybe we can come to the question section for all the audience.
Yeah. Thank you. So, question. Do you have any question and comments?
Yes. Can I ask?
Yes.
Hi, this is Yoshino. And so nice talk. I'd like to ask you about how when you extracted this effective Ising model from your trained neural network. So you had effective Ising model with JIJ and HI.
Yeah.
And so in this, so here are the Ising variables represent actually the couplings in the neural network, right?
Yeah. What do you mean? How do you mean what is how to construct the Ising model or effective?
No. My question is that so in this effective Ising model, you have JIJ.
Yes.
I wonder. So is it you have coupling between all bonds in like bonds in different layers, or you consider only coupling between?
No, it's you treat for example the wave connection of all the this is four level. You treat the 4 layers connection as a whole, and then you build a connections. The JIJ, it is the I and J can be arbitrary connection. It can be come from the last boundary, and you can come from the fourth boundary, and can come from the internal boundary. It's arbitrary. The coupling. Yeah.
I see. But somehow, oops, sorry. But somehow you analyze the difference between the internal layer and the layers closer to the boundaries.
Right boundary. But I emphasize, if you focus on the internal layer, and then the coupling just to restrict to the within this layer, the internal layer. That is, they cannot couple to the boundary, the right boundary and the left boundary. So that is, it depends on which part you focus. You can focus as a whole, and then you focus at distinct parts.
I see.
Yeah.
Another question that's in this network, I think in the internal layers, you can rotate the nodes.
You mean the permutation symmetry?
Yeah, permutation symmetry. Do you take care of that when you extract effective?
Yeah, we during the construction we have now take care of the permutation symmetry, because permutation symmetry can bring you the maybe another solution classes, and they satisfy the same test error. We actually in our this is the first construction we have now take the permutation symmetry into account, and maybe in the following analysis we try to think about how to take this into account. Maybe it also related to the geometry, the global view in the wave space, these important properties.
Because in the last part you also showed this shallow network, and I think in that case you don't have any internal layer. So
yeah.
So in that case, you don't have this problem of permutation symmetry.
Yeah. It is, yeah.
So I somehow expected that when you have a large number of constraints, even in the system with internal layers, the system eventually becomes too much constrained and behave like a shallow network.
Yeah.
So but in the last part, you show that even in the what you call under parameterization, the system still have a lot of freedom. But I expect if you give much more, even more constraints, in the end, the system should look like shallow network.
You mean the under parameterized?
Yeah. So if you increase alpha more, even in the system with internal layers, the system becomes too much constrained in the end, and it should behave like a shallow network.
Yeah. It may be, because if you increase alpha to some point, we expect there are some change of these landscapes to has a qualitative change of the landscapes. Still, we do not. Now we are still the sampling work still ongoing. We want to cover a range of the alpha and to see how this landscape there's a phase transition for these landscapes for this landscape with 4-layer neural networks. Yeah, this is also very intriguing. Maybe this has a connection with the double descent in the deep learning studies.
Yeah. Okay. So and also in some series, including mine, I send infinite and limit, so infinitely large bits. So that brings the artificial phase transition, which you don't expect in finite end system.
Yeah. Okay.
Thank you very much.
Thank you very much.
Can I ask a question? So you map the deep learning structure to the Ising model with two-body interactions. So you're assuming that some kind of property can be described by two-body system, or do you expect some specific properties that can not described by two-body interaction, and or we need higher
yeah, I think this is a very
models or and
yeah. We assume this is a first steps. Of course, in a practical deep network, maybe the way the connection in each layer it may be coupled with each other's has a maybe long range correlation, or maybe the correlation may be a high order. This is can appear in the practical maybe very modern architectures, but in our case, we want to study at the first level of the approximation. You think about our two-body interaction that can capture maybe I will show the maybe capture the high order correlation up to some point, right? And you can see that if you put the high three spin correlation and three spin correlation from data, and this is correlation doesn't fit by our model, but our model can reproduce a certain percentages. It means that we have still a certain predictive power for the high order correlations. So based on this, we hope our model can give some insights, can be retrieved some insights towards to understanding the realistic deep networks. So on the other hand is that if you consider the higher order correlations and then the Ising model, maybe not the higher order Ising model, it may be very challenging to fix because the number of the coupling of the interaction parameters may be increased combinatorily with the order of the correlations. But anyway, another point you can use some concept from the sparse modeling, and you can constrain the coupling just between a few connections. It is not a large number of connections, and then the number of the parameter to fix or to learn for the Ising model will be decreased significantly. And maybe in that sense, you can construct a sparse high order Ising model to test the hypothesis from these studies. I think it is still promising, I think.
Okay, thank you. Do you have any questions? So I have a very short question. So you show a picture of the SD as a function of D.
Yeah.
And in case of the underparameterized case, this one, intermediate layer cross to the upper bound, but it seems not symmetric. Is it the result of some kind of structure you're considering for analysis?
You mean the curve? It is not symmetry.
Yeah.
I think due to in our model has some bias. You can see our model, original model. Is no. This one, it has a bias. Except the field, it has also this bias. This bias can change the shape. It is not symmetric because if you change sigma to minus sigma, of course, it depends also on this part, right? Maybe. So this is not has a symmetry, intrinsic symmetry. It's it depends on how large of your local bias for each connection, each way in your deep network.
Thank you. So, do you have any questions? So, if there is no question, I will close this seminar. Okay.
Yeah, thank you.
Oh,
thank you all.
Please thank to Hansen for a nice talk.
Yeah, thank you.
Thank you so much.
Thank you for all your audience and to listen to my talk.